All right, let's do another problem. So this is actually the second problem of the day now. So this is number 54201 matrix. Given an m by n binary matrix mat, return the distance of the nearest zero for each cell. The distance between two adjacent cells is 1. And they want us to, let's see, so 0, 0, 0. Okay, and our output is pretty much the same. However, in the case of something like this one, yeah, 0, and then 0, 1, 0, 1, 1, 1, this bottom row here looks like it is distance 2 away, technically, diagonals not counting. This looks like a pretty good candidate for a BFS type thing. Because BFS will explore the nearest cells, and we can consider those as of distance 1. So let's see. We can say for each cell, or for each column in mat, then for each row in column, if the column cell value is 0, immediately return or write the value in the result as 0 because we're sitting on a 0, right? So then we don't have to do anything like that. We don't have to do anything extra, rather. If the column cell value is not 0, we need to perform a BFS on that. The problem then becomes, how do we determine let's see. Start here, that's 0, here, 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 and then here. I'm gonna be honest, BFS is one of those things that I wish I had more experience with, but unfortunately I just don't. So, let's try our best to see if we can do something that works. So, we'll add the cell into a queue. Right, and we'll start. So this is the first part. So this is just like just discovering, I guess, just like, yeah, discovering cells that need to be filled in. Then we can say while the queue is not empty, if the cell now has a non-zero value, because any cell that is in here will be non-zero. This is a small optimization that I think might help. Basically, the idea is that if we encounter a cell which has already been written with a distance from another cell, then, ooh, now that I think about it, there are two ways to go about this. We can either do a BFS from the cells which are not 0, or alternatively, we can do a BFS from the cells themselves. Right, or either the zeros or the non-zeros, right? If we do the zeros, we can sort of fill in all the cells. And the problem with that is that it would be m by n multiplied by the number of zeros in the cell, right? Whereas, honestly, I don't think actually it's that much different. You could do either of them. So you can choose to BFS from all 0 cells or BFS from all non-zero cells. Both will be O of m times n, so basically the size of the array, times, I guess I'll just put a hash there, where the hash is equal to either the number of 0 cells or non-zero cells. So it really depends on your array, on your 2D array, on which algorithm is actually faster. It would be marginally faster unless it's like incredibly skewed, right? But for the average case, both algorithms should be pretty much exactly the same runtime. So let's go back to our BFS. So while the queue is not empty, if the cell now has a non-zero value, we can just skip. Otherwise, add all adjacent, meaning 4-way adjacency, because we're not doing diagonals in this problem. Cells to be, or check all adjacent cells. If non-zero, check if non-zero plus 1 is less. If 0, set to 1. I'm not sure if this is actually valid. So if 0 is set to 1, I think that's pretty straightforward. Oop. Keyboard. If non-zero, check if the value in return or in result is non-zero. If yes, then see if add 1 is less than current. If not, then add to queue. So basically the idea is that if we have a non-zero cell that is next to us, so a cell that is 1 that is next to us, and it already has a value, then we can simply consider taking their value and adding 1. And actually we don't even need a check, because considering that it's BFS, there is really... That's a good question. Is there a situation where two BFSs on adjacent tiles would be... And I think there might be. So I'll keep this here for now, and then I'll come back to it later. Let's see. Check all non-adjacent or adjacent cells. If non-zero, then that. If 0, then set to 1. Cool. So I think this is actually pretty straightforward. And I guess technically you also have another O of m times n just added on to just do the initial discovery. Nothing too major though. So let's go ahead and get started with the code. So we'll say val return array is equal to array of type int array, which is of size mat dot. Mat.size. And then we can say mat.forEach indexed. This is column row reference, or call reference rather. And then we can say call reference for each row value. If value is 0, otherwise, and we're gonna have to have a queue, and we'll just say fill queue, and we can just use a mutable list in Kotlin of how do we define this reference? We can create a new class. We can say here, we can just have like a data class cell, eval row, which is an int, or column val row, which is also an int. Then we can say this is a queue or a list of cells, immutable list of cells, and then we can say fill queue dot add. We create a new cell with our column index and our row index. And then if the value is 0, then we can just say return array. Let's see. Return array at column at row is equal to 0. I'm not sure if this actually creates a 2D array. That'll be interesting. Let me actually just quickly do this just to see if there's any compilation errors with creating a 2D array like this. Yeah, that's unfortunate. Okay. What other ways can we create this? Expected one parameter. This would be an int. This would be an int array. This should be an int because it's the index. But this is not quite how you do it. Oh, that's a good question. I haven't really had to initialize a 2D array yet so far in Kotlin, I don't think. Let me think. Create an array of int array. No value pass for parameter in it. Okay. I think we need to do what we did in the previous question. Yeah, okay. So this needs to be mat.size, and then this is an init where we get the, I think this is the index, right? Then we create int array of size mat at index dot size. So this would be mat at column 0 dot size, and we can just one line this. And I think this actually creates our 2D array. Row expected one parameter of type int. Oh, this should be for each indexed. Indexed, not indexes. Okay, and then I think this is actually fine. Cool. Yep, okay, so that creates our 2D array. That's actually pretty nice. I love Kotlin sometimes. Okay, cool. So now, while not fill q dot is empty, what we want to do is that if, let's see, we'll take the valve first head is equal to, or we'll say front, right, is equal to fill q dot first. And we can say fill q dot remove at 0, so that just removes it. So while the fill queue is not empty, we'll say when, or let's see, we'll create a var has found 0 in adjacent square. We'll set that as false first. If mat at so front call -1 is greater than 0, greater than or equal to 0, and mat at front call front, I said column. Oh, why is this capitalized? No. Column row. Dot row is 0. Then this is going to be a lot of code duplication. Technically, I could just have this in one big fat OR statement. And actually, I think that's what I'm going to do. So this OR front.column +1 is less than mat.size, and mat at front column +1, this should be front column -1, front row is 0, or this needs to be wrapped. This is gonna be a fat friggin' front.column. We can say, let's see, front.row -1 is greater than equal to mat front.column dot size, or -1 is greater than 0 still, and mat front column front row -1 is 0, or last one, front row +1 is less than mat at front column dot size, and mat front dot column front dot row +1 is equal to 0. Then return array at column row is equal to 1. Otherwise, let's see. So we want the 4 cardinal directions. And then essentially we want to say, okay, if not, then we want to add the rest of them to the queue. We want to add them to the queue, and then we want to continue on from there, as long as they're not a non-zero. So we can, let's see. If I did this, right, this, it would find a 0 in one of the cardinal directions, so that's just 1. Here, same story. here would not be the same story, right? And here would be the same story, but here would not be the same story. So 1, 2, 3, all three of these are non-zero. Is there a case in which there is a a larger and a smaller one? I think yes, because if we had a 1 here, then from here the distance would be 1, 2, or 1, 2, 3, right? So 1, 2, 3, or 1, 2. So we can choose basically if the value is a 1, we can choose the minimum among values that we have in our area against ones in our area that are non-zero. So the problem is that this logic, I feel like we're gonna have a little bit of duplicate logic. We're going to say val top is going to be front.column. Do we want to just run a BFS? Because we would hit the top first, then here, then here. I have a feeling that there's gonna be that this is gonna be a situation where like something just doesn't get filled right. We'll see. But actually, first, before we do that, let's actually go ahead and test out this code first. This code should return correctly for the first example. Let's see, return array at column. Oh, this needs to be front.column, front.row. Right. This should return correctly for the first one, and it did. So now we need to figure out the rest of them. Really, the idea is just like we need to figure out like how we can get the most optimal solution from all of these. Because it's an m by n array, so it can be longer on one side or like something like that, right? So it's not perfectly square, so there's no assumptions that we can make from there. But really the question is just that like it can be imbalanced. It can be very much imbalanced. I'm just thinking like, okay, if it's imbalanced, then is there a way that we can sort of make sure that we get the most balanced item? Let's say so this sets to 1, this sets to 1. Or let's say that we had let's take that example that I was mentioning before with the unevenness. So it was 0, 0, 0, 0, 1, 1, 1, 1, 1. And this would translate to, on the board level for the return, 0, 0, 0, because it starts with that one, 0, 1, 1, right? Or let's just leave those as blank first, just to show that those are not there. Okay. Then it would start at the center because that's the first item that we encountered. So that'd be 0, 1, blank. And then this would be 0, 1. This would also be 1 because there's a 0 there. This would also be a 1 because there's a 0 nearby. This is where the fun is. So this has no value. So we can say val top is equal to if front dot column plus 1 is greater than or equal to 0, and return array at front dot column plus 1. Actually, it should be minus 1. Front row is not 0. Then we do a return array front column minus 1 front row, else oh gosh, because there's 4 to evaluate, right? Okay. Else we can do math.maxValue, or I think it's integer. Basically want to use the Java max value for that. And let's do some duplication. This is bottom, this would be left, this would be right. Plus 1 is less than, we want to say mat.size. And we want to make sure that it's a non-zero value in there. Otherwise, of course, 0 would be the best. Front. We need to do mat at front dot column, front dot row or dot size. And similarly, the same thing here. Plus 1 is less than mat front column size. And here, row minus 1, row plus 1, and then this would be column plus 1, this would be a row minus 1, this would be row plus 1. I think that makes sense. If mat front column size is less than that, and right, we can make this front dot row plus 1. And same for here. Front dot row. If front dot row is less than mat column dot size outside of that, and return array row is not 0. Yep. Then we basically need to check the minimum of all of these. So find the minimum of them all. There's at least 1 0 in mat. That's good to know. Would this pose a problem if the 0 is all the way at the bottom, though? I see. Right, because if the 0 is at the bottom, then you'd have basically just a bunch of holes in here. This would be like that. Right, and you start from the top right, but that doesn't make sense. Okay, so I guess in that case then, you really need to, you probably do need to do the zeros style then. Interesting, okay. So what we'll do instead is that if the value is 0, we'll set the return array there, and then we'll just start with the fill queue dot add column. Because basically it kind of feels like we need to do like a almost like a flood fill type thing for the array for the 2D array. We need to create a new, not column, we need to create a new cell with the appropriate column and the appropriate row. So now what we want to do is that we want to basically just if the value is currently 0, so if basically the front dot column -1 is greater than or equals 0, and the value in the actual array is not 0, so this is a non-zero top. And then at this point we would need to say check to see if this if our current we want to check to see if our current sort of area, if the current cell's value is greater than our current depth +1. Or, sorry, is less than. If yes, replace. If not, don't. That's pretty much that, but it seems like a little bit complicated to implement. Let's just think about it some more. We don't need that. Because now we need to, the main question that I have right now is like, how do we keep track of our current situation with our BFS, right? We don't know our distance from our 0. We don't really know our distance from 0 without having additional state. So I think we kind of need to extend this, and we can say class BFS fill. And what this class will have it'll have a val items to fill, which is a list, a mutable list of cells, and it will have a var current depth, which is an integer. Basically, this keeps track of our current depth, right? And let's see. And we can say while not front is empty, the first item is always the 0 we want to branch from, because we're going to be creating this here. We'll create a BFS fill of starting at this cell and of depth 0. val current cell is equal to, let's see. This is complicated. This almost feels like a DFS, like a recursive approach would work a lot better. But I think a BFS just feels right. I don't know. Maybe I'm incorrect in that sort of sense, but a BFS feels more right in this case. The problem then is like, how do we recalculate our depth? We add in a new item. We add in a new BFS fill with the 0. But how do we terminate this? Oh, there's so many questions now. It's doesn't seem like it's like the more that I look into this problem, the more sort of questions that I have. So I guess one is like, how do we terminate this condition with the BFS if we keep on adding adjacent cells? A potential solution is that if we replace then we add to the list because we might proliferate it. The idea is that if a cell is replaced, then its adjacent cells can probably be one better. If we don't replace it, then it's the best that it can be, and we don't need to worry about the other cells. I'm not sure if this is actually logically sound, but this is what I'm going to go with for now. The second question is, I guess like following the others, this can just be a list. Sorry, no, this items to fill needs to be a list of, did not mean to do that. Just skipped right out of the page. So we just create a list of one item inside the fill queue, which takes BFS fill items. Front fill. And then what we basically do is that we will run these checks across all 4 of them. Of course, we need to also make sure let's see. So we set the value there. And as long as it's a non-zero, because we don't want to add non-zeros regardless, right? So we answered the question of keeping track of the situation. Let's see. So we have our top value. We know that it's not 0. If, let's see. front fill val current cell is front fill dot first. And then we'll probably need to remove it, so front fill remove at 0. If the current cell in the return array column current cell dot row plus 1 is greater than or is less than our return array at front, or what would this be? Actually, if current, what is this? Current cell dot current depth, right? Plus 1 is less than our pretty much the return array of this cell. Or we can say if return array current cell dot column current cell dot row is 0 or the value is greater, then we can say return array that is equal to current depth plus 1. Current cell. No. It's front fill. Because this is of type cell. So we need to replace current cell here, current cell here. So what we can do is that we start at the 0. We check all 4 spots for non-zeros. If there is a non-zero, if the value of that non-zero, if their current cell current row oh no, these are the other cells, right? Column -1. Return array current cell column current cell row is less than that. Then we want to set the value to our current depth. Return array current cell column current cell row. Right? So basically we can get rid of this and do that. We can just replace this with that. And honestly, we can get rid of this. Rather than doing this, we want a mutable list the cells that we want to fill the neighbors of. Which is fine. So in that case, we don't need this. Oop. So while the fill queue is empty, we can turn that into there. Right? This is of type cell. This is our cell within here. We can say that the value is 0, or if the value is 0 currently in that area, or if our current depth, which is the depth of our current cell in compared to that one, is less than what they have, then we set it, and then we want to proliferate it. So fillQ.add fillQ, or not fillQ, cell of, let's see, it would be current cell dot column minus 1 current cell row. Pretty much this. Copy and paste a couple times. If we add 1 and that is greater or less than the material size, or this plus 1, this is a plus 1, plus 1, plus 1, plus 1. Right, we're just adding this. And now we want to say if current cell dot row minus 1, row minus 1, this is a non-zero bottom, non-zero left, non-zero right. Oh, I don't think I finished replacing this. This is minus 1 here, minus 1 here. Pretty much doing the same thing, you know. Just replacing the minus 1s and getting the DFS sort of in place for adding the stuff. Less than mat size. No, not mat size. Mat at current cell dot column dot size. It's a little bit funky. Plus 1. This plus 1. Plus 1. Plus 1. Plus 1. Yep, so basically it's pretty straightforward. We add the item, or we start at the zeros, right? We go through the m by n array. We find all zeros. Then for each 0, we find any non-zero item, any non-zero cell. And if the non-zero cell happens to have a current if it has a current return array value of 0, which is impossible, so that's like technically uninitialized, or the current depth of our array, which we have in our return array current cell column row, is less than what it has currently, then we set it within the return array column, appropriate column. And then we also add it to proliferate the changes to anywhere else that we need. This is effectively like a you can think of this as like quote unquote like flood fill, but yeah, this is effectively flood fill, but you just proliferate the values. And then we just do the same thing for the other ones. So that was the bottom. This is the top. This is the bottom. This is the left. This is the right. And then at the end, we just remove that cell from the queue, and then we continue there. So I think this array works because we're going through all of the zeros. So if there is a more optimal zero for a particular cell, it will get proliferated, or it should get proliferated through its neighbors. Because if a neighbor has a more efficient path, then it should return, or it should get replaced, and it should proliferate on. And then that sort of just goes through the entire thing. Let's use the other example test case just to make sure that, just for like a basic sanity check. And then we'll go through and we'll run a submit if this works, okay? So again, this is O of m times n for the first part because we're just adding the zeros to the queue. Then this is also O of m times n times the number of zeros that we have. So this would be a lot less efficient if there are a lot of zeros in our matrix. So let's give it a submit and let's see if there's anything that we need to fix, or if there's anything, or if our speed is just particularly slow. And surprisingly not. The runtime is 570 milliseconds faster than 88.3%, and our memory usage is 89%. So that's actually like pretty damn good. And honestly, I'm pretty I'm happy that I managed to remember what BFS is like, because that would have been a bit of an oof moment if I didn't. But in any case, it looks like we did a decent enough job. And yeah, in any case, I hope you learned something, and I will see you for the next problem.